Today's lesson is going to be about combinations of functions. As you can see here, we've got 4 different types of ways that we can combine functions, and it's just the 4 basic operations. We have addition, subtraction, multiplication, and division. What we're going to be doing today can basically be summed up as I'm going to be giving you 2 functions and asking you to combine those 2 functions using one of these 4 operations. So, as you can see, with our first combination, a sum, that means if I give you an f of x function and a g of x function, I'm going to ask you to take those two and add them together. Same addition rules as we've always had, so you're basically just going to be combining like terms. Then we've got the difference, which means you're going to be taking an f of x function and g of x function and subtracting them. Now with these, it is important that you're paying attention to your order, right? Because if I say you're taking f minus g, then that means you need to make sure the f of x function is coming first, minus the g of x function coming second. After that, we've got the product, which means you're going to be taking 2 functions and multiplying them together. Recognize that will be different depending on how you're doing it. It could be a simple distributive property. You could be having to FOIL out. There could be a lot of work depending on how many terms you have in there. And then finally, we've got the quotient, meaning you're going to be dividing. Again, for this one, order is important because if it's f over g, you need to make sure the f of x function is in your numerator and the g of x function is in your denominator. Now, considering these are functions and they're going to likely have, some variables in them, with dividing, what you're really going to be doing is basically looking to factor the numerator and factor the denominator, and then see if anything happens to simplify that you can cancel out, reduce down. There may be a fair amount of times where you don't have much you can do with the quotient combination. Do notice that our quotient combination has an extra looking piece here. The g of x does not equal 0. Remember, that is simply just a reminder that if you get 0 in the denominator, that would cause that fraction, that expression, to become undefined. You cannot have 0 in the denominator. You cannot divide by 0. So that's all that's reminding. So, for an example, let's say we had an f of x function. Let's say I gave you an f of x function that was 3x plus 4, and a g of x function that was x squared minus 5x plus 2. And let's say I asked you to do f plus, actually I'll change the colors there. Let's say I asked you to do f plus g of x. Meaning, I am asking you to take the f of x function and add that to the g of x function, right? Recognize you could see it written this way, or I could just as simply write it like this. Both of these mean the exact same thing. It's not changing what you're going to do here, okay? So whichever way you look at this, if we are taking f of x plus g of x, that means I would have the quantity of 3x plus 4, meaning the f of x function, and I'm supposed to be adding that to the quantity of x squared minus 5x plus 2, my g of x function. Well, since it's addition, there's really no need for those parentheses, right? Addition, we don't have anything to distribute. I mean, you could distribute this as a positive 1, I guess, if you wanted to, but the reality is we don't need those parentheses. So really, we're just taking a 3x plus 4 plus an x squared minus 5x plus 2, which means I just need to combine like terms. So I only see a single x squared term, so I'm just going to rewrite that. I see both a 3x and a negative 5x. Those are both like terms. I can combine them. 3 minus 5 would give me a negative 2x. Along with that, I see a positive 4 and a positive 2 that are both constants and therefore like terms. So I'd take 4 plus 2 to give me 6. That would be your f plus g of x. That would be your answer for this example. This time,
let's say I give you the same two functions, the f of x and the g of x function, but I'm asking you to do f minus g of x, meaning I'm asking you to take the f of x function and subtract it by the g of x function. So we still have our f of x function of 3x plus 4, and then we're taking that minus our g of x function of x squared minus 5x plus 2. So really the only special thing with this one compared to the addition is if we are subtracting the entire g of x function, then we want to make sure this negative is being distributed to every single term from the g of x function. Meaning what we're really doing here is taking 3x plus 4 minus an x squared plus a 5x because of the double negative, and then minus 2. Once we've done that, it is pretty much going to be the same the rest of the way as the addition. We just want to combine our like terms. So I have a negative x squared term this time, but I don't see any other x squared terms, so I'm just going to rewrite that. I have a positive 3x term and a positive 5x term this time. 3x plus 5x would give me 8x. And then I have a positive 4 constant and a negative 2 constant. 4 minus 2 would give us a positive 2. So that would be our answer for f minus g. Now let's say I ask you to take f times g of x, meaning I want you to take f of x and multiply that with the entire g of x function. Well, just like we've been doing then, for the f of x function, that being 3x plus 4, that means we are taking the quantity of 3x plus 4, and we want to multiply that with our g of x, which is the quantity x squared minus 5x plus 2. So this is going to take a little bit more time than the other two examples that we've done, because multiplication just by nature with polynomials takes a little bit longer. So basically what we're looking at here is a double distributive property, right? I need to take 3x and I need to distribute it to everything in the g of x function, the second parentheses, and then I'm going to need to do the same thing with 4. So 3x times x squared would be 3x to the third. 3x times negative 5x would be negative 15x squared. 3 times negative 5 is negative 15. X times x is x squared. 3x times 2 would be 6x. 3 times 2 is 6, right? Then I need to do the same thing with the positive 4. 4 times x squared is 4x squared. 4 times negative 5x is negative 20x. And 4 times positive 2 would be positive 8. Now that we've done all our distributing, all our multiplication, we just need to combine our like terms. I only see a single x to the third term, so I'm just going to rewrite that. I see a negative 15x squared and a positive 4x squared. So negative 15 plus 4 would be negative 11x squared. I see a positive 6x and a negative 20x. 6x minus 20x would be a negative 14x. And then I don't see any other constants besides the 8, so I'm just going to rewrite that. So it looks like that would be our answer for f times g of x. Finally, let's talk about quotient. Let's talk about taking f divided by g. So in this case, if I'm taking f divided by g of x, that means I'm asking you to take your f of x function and put it over or divide it by the g of x function. Which means, in this scenario, we would have 3x plus 4 over x squared minus 5x plus 2. So at this point, there is nothing we can do to simplify, which that's what we're looking to do, is see if we can simplify, if we can reduce this expression down. We don't have anything that we can do that for. But before we say we're done, we need to check and make sure that we can't simplify the numerator or denominator, or factor the numerator or denominator in any way. Well, 3x plus 4, the only thing we could do with that would be GCF, greatest common factor, and there isn't one, so there's nothing to do there. x squared minus 5x plus 2, that's a trinomial. So it's possible we could factor that by, for example, trying to use the x method. So 1 times 2, a times c is 2. B value of negative 5, so we would need to find two numbers that multiply to positive 2 but add to negative 5. I don't believe there are any numbers that do that, which means this denominator is unfactorable, and so that means there is nothing to cancel out. We would just have to stick with this expression right here. There is nothing we can do. And you may find a fair amount of f divided by g's, g's divided by f's of quotient combinations that end up like this, where there really isn't anything to do. Just to show you an example of what it could look like if you were actually able to simplify, let's say I gave you an f of x function of x plus 2 and a g of x function of x squared minus 4 and asked you to take f divided by g. Well, in that case then, that would mean you'd have x plus 2 as your numerator divided by x squared minus 4 as your denominator. And so again, right now we can't reduce anything, we can't simplify, but we want to look and see if we can factor the numerator and denominator. The numerator can't be factored any more than it already is. X plus 2 is just x plus 2. But our denominator of x squared minus 4, that would be a difference of two squares. So remember the way that works is since there's two terms with subtraction between them, and they can both square root perfectly, I am able to factor this. The square root of x squared is x. The square root of 4 is 2. So we'd have x plus 2 and x minus 2. If you prefer doing it off the x method, you could also think of this as looking for two numbers that multiply to negative 4 but add to 0 because we're missing a b value there. Either way, you get the factor of x plus 2, x minus 2. And so now we can see that we have an expression of x plus 2 both in our numerator and our denominator, which would allow us to cancel those out, giving us a final answer of 1 over x minus 2. So that's what could happen if you do happen to have a numerator or denominator that can factor, or maybe even both can factor. But that's why you always got to check.